Hello, welcome to module 10. In this module, we're going to talk about another new technique that you can use to test a software, which is called graph coverage. Okay, so let's get started. I have shown you this diagram before that we can test the software based on several structures that we can use. So we have discussed input space that we use ISP technique to do input space partitioning. And now today we're gonna discuss this technique called graph-based technique, which you can apply to the source code, to the design, to the spec, and also to the use cases of the software. The next one would be the logic-based, which we're gonna study in the next few modules. And the syntax-based one is the one that we are not gonna study in this class. Okay, so if you look in terms of the RIPR model, the input space partitioning only give you the last R, which is reveal. We cannot have much control on whether this bug will go into the right location, and we cannot control whether it's going to infect the faulty location in the source code, and also we cannot guarantee that it will propagate to the final output. Okay, so for input space partitioning, it works in some certain cases, but if you want something that is more fine-grained and we have more control, then we move to the more detailed version of the structured criteria-based testing. For the graph-based technique, we can get the first R, which is reach, and the last R, which is reveal. Okay, so we can specify the input to reach the faulty location exactly, and then we can know that this will reveal the fault to the output, and then the developer can spot it. All right. Okay, so today we're gonna talk about one of the most widely used test coverage criteria, which is graph coverage. And then we start by talking about some basic theory of graph. What are graph? What are nodes? What are edges? And what are their properties? And then we're going to discuss how to use these following criteria to design tests, including node coverage criteria, edge coverage criteria, edge pair coverage criteria, and prime path coverage criteria. All right. So let's get started with the basic concepts of graph. Graph is one of the most commonly used structure for testing. It can also be used for many other kinds of computation as well. For testing, we derive the graph from many sources, including control flow graph from the source, design structure, finite state machine, or some state charts or use cases that you have. And the graph, it doesn't fully represent the artifact or the software under test. It omits some of the details. So you won't care about how the code is written, but you care about the structure of the code based on the graph structure. So with this kind of structure or representation of your software, we must define the test to cover the graph in some way. Usually we would do this by traversing some specific portions of the graph, and we make sure that it covers based on some specific criteria that we set. Okay, so the two main components that you have in graph is nodes and edges. Okay, so the node will represent a statement in a program, not a statement, sorry, a set of statements in the program, or it can represent a state in a program. It can represent a method, or it can represent a basic block in the program. We're going to talk about this soon. The edge represents a branch. For example, if you have some if-else or some transition of the program or a method call. All right. So let's start with some basic notion of the graph. When I say nodes, I would use the symbol capital N to represent a set of nodes. And N must not be empty. So a graph must have at least one node. Okay, at least one node must exist to be a graph. And then we have a special type of node, two types of special nodes. The first one is called initial nodes, and we use the symbol n subscripted 0, n0, to show that this is a set of initial nodes. Also, the set of initial node must not be empty as well. And you can have many entries or you can have just one single entry. The third one is called final nodes. The final node, we represent that set using n subscripted f or nf. F stands for final. This is a set of the final nodes. And also, it must not be empty as well. And we can have the graph that has multiple exits, or it can have just one single exit. For the edge, we use capital E to represent a set of edges. The edge will connect one node to the other, and we write the edge as a pair of nodes. This is a starting node, Ni, starting. And this is an ending node, Nj. Okay? We call Ni as a predecessor. Pre means something that comes before. So Ni is the starting one, is called predecessor node. And Nj is a successor node. Success come after. So it's the node that come after the starting node, right? And every test that we do, it must start in some initial node and it must end in some of the final node. That is because we must have the way to provide the test input. That where we get the initial node. And we need to observe the output. So we need to see the end. We need to go to the final node. If the graph it doesn't satisfy initial node and ending node criteria, the final node criteria, then we cannot test them. And this kind of final node depends on the software artifact that the graph represents. And usually the test criteria, as we already discussed, it requires the test to end on a particular final node. So some of the final node we might not care about, but some of the main final node we might put more focus on. And some test criteria might be a little bit more flexible, where can be any final node that the test end. So anything inside of this NF is okay. All right. So in this diagram, I show you an example graph. So this is a graph containing 4 nodes, 1, 2, 3, and 4. Okay. The set of node n consists of 1, 2, 3, and 4. The initial node is 1, which is this one, right? How do we know it's an initial node? It has this special arrow pointing in. So that's called initial node. We have one final node, 4. The final node is shown by having this double-edged circle, and it also has only incoming edges, but without any outgoing edges. So when it stops, you don't have any outgoing edges. So the set of NF is 4, all right? When we look at the set of edges, we will see that there's a first edge from 1 to 2, okay, which is this one. The next one, 1, 2, 3, which is this one. The next one is 2 to 4, which is this one. And the next one is 3 to 4, which is this one. So this graph has also 4 edges. Okay? It has 4 nodes and it also has 4 edges. So quick question now is that if you look at this graph, it has just one node. And that node is an initial node because it has an arrow coming in. It's also a final node because it is the end of the everything. It doesn't have any outgoing edges and it doesn't have any edges. Is this considered a graph based on the definition that we just discussed? You can pause the video for a few seconds, think about it, and then resume. All right, so the answer is yes, because this graph has at least one node. The definition doesn't say that the graph must have at least one edge, right? But it says that it must have a node. it must have an initial node and it must have a final node. So this graph actually satisfies the conditions to be a graph. This one, I show you another kind of graph. This is called multiple entry, multiple exit graph. We can see that there are many incoming edges. So these are all initial nodes. And there are many nodes that the execution ends without having any outgoing edges. So these are the final nodes, right? So if we list them, we will see that there are 10 nodes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. For the set of initial node, we have the node 1, node 2, and node 3. For the final node, we have the node 8, 9, and 10. And when we look at the edges, we need to also see the direction of the edge so that you can write the edge correctly. So this one is 1, 4. This one is 1, 5. This one is 2, 5. This one is 6, 2. Okay. This one is 3, 6. This one is 3, 7. This one is 4, 8. This one is 5, 8. This one is 5, 9. This one is 6, 10. This one is 7, 10. And the last one is 9, 6. All right, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 edges here. Okay. So with this one, you can have many ways to come in. You can come in during using this one and come here, or you can come in using this one and in here. Okay. Another graph. So this graph, if we analyze the composition, we will see that first it has 4 nodes, 1, 2, 3, 4, just like the previous two previous one that I showed before. There is no initial node, and there is one final node, 4. The edge is the same, 1, 2, 1, 3, 2, 4, and 3, 4. So in this case, this one is not a valid graph because based on the definition, it must have at least one initial node, one final node, right? So this one has no initial node, so it is not a valid graph for our testing, and it is not useful for generating test cases because we cannot provide the test inputs. Okay, we already know about nodes, we already know about edges. So the next one is the concept about paths. So what are paths? Path is a sequence of nodes. Okay, we usually represent a path using the symbol P. And the sequence of node is written like this. We use a bracket followed by the first node, the second node, continue to the last node in that path. Think about a path like you go through from one location to another location to another location until you reach the destination. And this one forms by having multiple edges. Okay, so in each of the path, you would have many set of edges continuing from each other. So each pair of the adjacent nodes, such as ni and ni plus 1, will be an edge in the graph. The length of a path is the number of edges. Okay, I want to emphasize here, it's not the number of nodes, but it's the number of edges. So think about it as how many hops that you need to do. So for example, if you have this and this and this, you need to do 1 hop, 2 hops. So this is a length of 2. Sorry. Okay. If you have one single node, like this one, it will have the length of 0 because it doesn't have any edge, right? So it's no edge. And when I call a subpath is a subsequence of the nodes in P. Okay, so if I have a path, let's say 1, 2, 3, 4, a subpath would be 1, 2, 1, 2, 3, so on and so on. Okay, so the subpath can be many, and the P itself is also the subpath of itself because it contains the same subsequence of nodes. All right. So when we go back to this kind of graph, let's analyze the path here. From this graph, we can have many paths. So the first one is 1, 4, 8, and then you get this path. The second one is 2, 5, 8. You get this path. The next one is 2, 5, 9, and you get this path. You can have a longer path by going to 2, 5, 9, 6, 10, okay, which is this one. And 3, 6, 10, which is this one. If you come the other way, 3, 7, 10 is this one. 3, 6, 2, 5, 9, and it is this one. And you can keep going on and on. And we can see that in some situation, you might get a cycle, which means you can just keep going until you come back to the same point, and then you can keep continuing. So 2, 5, 9, 6, 2. And if you want, you can go another round. And if you want, you can keep going another round. So this thing is called a cycle, when you can go through the path in circle and you can just keep going in that loop. So a cycle is a path that begins and ends at the same node. Okay, we will see that this one begins at 2 and it ends at 2. Okay, so whenever there's a cycle, you have one complete loop like this. Okay. If you don't get the correct sequence of nodes inside the graph, then it is not considered as a path. For example, 1, 8 is not a path because you cannot find any location from 1 to 8. Okay, so this is not a path. Next one, 4, 5. You start from 4, 5 is here. You cannot go to 5, right? So this is also not a valid path. The next one is 3, 7, 9. 3, 7, but 9 is here, and we don't have any path going to 9. So this is also not a path. So to summarize, invalid path is a path where the two nodes are not connected by an edge. In this case, 1 and 8 is not connected. This one, 4 and 5 is not connected. This one, 7 and 9 is not connected. So whenever you find the path that there are two nodes that are disconnected, then we can call them invalid path. This invalid path can occur in the real software. So study this program on the left. Okay, so this is a program to check some value in the number. And if you look closely at this location, okay, we can see that the condition here will be the condition that will never be executed, okay? Because the conditions say that if num2 greater than 4, but if we consider the if statement before that, if num2 greater than 3, so whenever num2 is larger than 3, you will always do this one, and it will never reach this location because num2, which also already more than 3, will never be greater than 4 again. So if we convert that into a graph, we would get a graph that looks something like this. And that location is here, where we have the condition of num2 more than 4. And we can see that this will never be reached. So if you go this way, you will always, if you go this way, you will always go here, and then you will always go here. But if you come this way, you need to always come here. So this one will never be reached in practice. All right, so this is an invalid path that you cannot go. And when we do the actual testing, we want the input to go from one node and end at another node after you execute the test. And when we do on the real software program, we can find that some path, they cannot be executed like what we showed before. So that one, we cannot actually explore those specific locations in the program, okay? Another example is that a path that demands the loop to be executed 0 times, but the program actually always execute the loop at least once. So in this case, you cannot find the path. You cannot make this kind of path happen anyway. So this thing is based on the semantic of the software artifact and the graph that represents such software. Okay, so we're now gonna only emphasize on the syntax of the graph, and then later we can see whether there are invalid paths in the graph or not. So the next concept is called graph reachability and test paths. Okay, let's start with graph reachability first. Reachability means that you can reach some certain nodes in the graph. So a location in a graph, which can be either nodes or edges, can be reached from another location if there is a sequence of edges from the first location to the second. So let's say we can find a path from to that location. Okay, so if you can find a path to that specific location, we say that location is reachable. And there are 2 types of reachability. The first one is called syntactically reachable, which means you have a subpath from node Ni to node N that you want to go, or to the edge that you want to go. And the second one is called semantically reachable, which means you can actually find a test that execute that subpath. You might get some invalid path, and then you cannot actually do it using tests. So that is not semantically reachable, although it might be syntactically reachable. So let's do some quick exercise on the reachability. If we have this graph again, the multiple entry, multiple exit graph, and we want to test that from node 1, where can be reachable from node 1. From node 1, we can go to node 4, we can go to node 5, I can go to node 8, I can go to node, I can go to node 8 again using this path. I can go to node 9, I can go to node 6, I can go to node 2, can I go to node 10? I go here, can I go to node 7? No, I cannot, right? So I cannot go to node 7. I also cannot go to node 3, okay? So from node 1, I can reach all the nodes except node 3 and node 7. So let's move to node 5. If I start from node 5, I can reach node 8. I can reach node 9. I can reach node 6. I can reach node 2. I can reach node 10. But I cannot reach the node 1, 3, 4, and 7 because I cannot go to 4. I cannot go to 1 because this is like different direction, right? I cannot go to 3 as well. And I cannot go to 7. Okay, so from node 5, I reach all the nodes except node 1, 3, 4, and 7. Next, let's start from the edge 7, 10, this one. From the edge 7, 10, I can reach node 7, which is this one. I can reach the node 10, and I reach my edge itself. But then the rest, I cannot go anywhere. I cannot reach any nodes or any edges in this graph. So from edge 7, 10, I can reach only these components, okay? And some of the graph, you can also have some edges from a node to itself, something like this. Okay, so that is also possible to have the edge coming back to itself. The next one is called the concept of test paths. So the test path is a path. Okay, so the first thing is that it must be a path. It's a path that starts at an initial node and end at a final node. So it's a special type of path that must start at initial node and it must end at a final node. This represents the execution of test cases, because when you have a test cases, you must give the input here and you must observe the output here, right? So when we do tests, we need to do test paths, because if you don't have the initial node and you don't have the final node, we cannot give input and we cannot observe the output. Some test path can be executed by many test cases. Some test path cannot be executed by any test cases. That's possible as well. And some test path cannot be executed because they are infeasible to do, like the invalid paths. So if we have this graph, okay, this graph is called single entry, single exit graph. The single entry, because it has only one entry in and it has only one final node. So it's like single entry and single exit. With this kind of graph, the initial node set has exactly one node. And the final node set also have exactly one node. It is possible that the final node can be the same as the initial node as well when you have only one node graph, right? And the final node must be syntactically reachable from every node in N. What does it mean? From every node, you can go to the final node here. So from 1, I can go here. From 2, I can go here. From 3, I can go here or here. From 4, I can go here. From 4, I can go here. And from 5 and 6, I can go this way and this way. And then there's no node in the end that can be reachable from this final node. Okay, so from this one, you cannot go back to any other node. It's one way from left to right. So this single entry, single exit graph sometimes can be called a double diamonded graph. Okay, and usually it represents the two if then else statement in your program. So within this graph, we have 4 test paths. Okay, the first one, 1, 2, 4, 5, 7, 1, 2, 4, 5, 7. The second one, 1, 2, 4, 6, 7, 1, 2, 4, 6, 7. The third one, 1, 3, 4, 5, 7. And the last one, 1, 3, 4, 6, 7. Okay. We have only 4 test paths because when we consider the test path, we must start at the initial node and we must end at the final node. So the initial node always be 1 in this case, and the final node will always be 7 in this case because it's single entry and single exit graph. Next is a concept called visiting. So if you have a test path P will visit any node if that node is in the path. Similarly, the test path P will visit any edge if that edge is also in the path P. Okay, so we have this single entry, single exit graph again. We have 7 nodes and we have 1, 2, 3, 4, 5, 6, 7, 8 edges. If we consider the path 1, 2, 4, 5, 7, it will visit the node 1, 2, 4, 5, and 7. And it will visit the edges 1, 2, 2, 4, 4, 5, and 5, 7. Okay, because these nodes and these edges are in the path that we are considering. The next one is called tour. So a test path P will tour a subpath Q if that Q is a subpath of P. Okay, if Q is shorter than P, we call that the path P towards the subpath Q. Looking at the same graph again, we have the same set of nodes and the same set of edges. If we consider the test part 1, 2, 3, 4, 5, 7, it visits the following nodes, it visits the following edges, and it tours the following subpart, which is itself 1, 2, 3, 4, 5, 7, smaller version 1, 2, 4, 5, 2, 4, 5, 7. So 1, 2, 4, 5 is this one. Oh, sorry. I think I better use the laser. So 1, 2, 4, 5 is 1, 2, 4, 5. 2, 4, 5, 7 is 2, 4, 5, 7. 1, 2, 4 is 1, 2, 4. 2, 4, 5 is 2, 4, 5. 4, 5, 7 is 4, 5, 7. 1, 2 is 1, 2. 2, 4 is 2, 4. 4, 5 is 4, 5. 5, 7 is 5, 7. Actually, I think we missed the part with only one node as well. So 1, 2, 4, 5, and 7. Okay, so that's all the parts that has been toured by the test part P. Okay, and any given part P will always tour itself. In this case, we show it here. Okay, because the part is a subpart of itself as well, so it always tour itself. The next one is that when we have the test cases, how can we map them to the test part? We call the test part, we call the part T as a test part that execute by test case T. And the part of capital T are a set of test parts that are executed by the whole set of tests T. Okay. Again, the test part is a complete execution from a starting node to a final node, right? So the minimal set of test part is the fewest test part that satisfy the test requirement, which means you visit all the test parts that are needed for that program. And this kind of mapping between test cases to the actual test part in the program can be in many ways. You can have many-to-one mapping where multiple test cases map to the same test part. Or you can have many-to-many mapping that one test case can go through many test parts. How can this occur? The test where the test can be mapped to multiple test parts can be possible because you can have some non-deterministic software. The software that contains randomization, software that rely on some other external inputs, they can behave in different ways depending on the value or the input at that particular time. So the same test can be executed differently based on the input. So this can have many-to-many mapping. But if you have a deterministic software, when you give one input, the software will always do exactly the same execution. Then you get the many-to-one mapping. Or you can even have a one-to-one mapping. Okay. All right. So before ending this part, I want to go through this simple exercise. So if we have this kind of mapping between the test cases and the test part, okay, the graph starts here at node 1. It checks whether if A is less than B, if A equals B, or if A is greater than B. If A is less than B, then it goes to node 2, and then it goes to node 4, and then it finishes at node 3. If A equals B, it just goes to node 4 and then finish at node 3. If A is more than B, then it just goes to finish at node 3. So in this case, if we have the test case 1, A 0, B 1, which is A is less than B, right? It will map to the test part P1 of 1, 2, 4, 3. 1, 2, 4, 3. The second one, test case T2, we have A1, B1. So in this case, A equals B. It will come from 1, 4, 3. And the last one, test case T3. A is 2 and B is 1. So this one is A greater than B. It will just come from 1, 2, 3 here. Okay, so you can see that we have 3 test cases, and each one of them map to 3 different test parts. So this is 1 to 1 mapping. Okay, and this is pretty much it for this part, and we continue the second part of this module in the next video. See you in the next video.